How do I know if it's recording? Oh, it's recording, I think.
It said so.
I didn't hear that, but okay. So, okay, should we do all of the questions? Or at least, I'm gonna do most of the questions. I'll do the hard questions. And you guys define what the hard questions are. What do you want me to go over?
All of
Don't say all of them. I don't have that kind of time. It's past my bedtime. I need to be asleep now. Okay, maybe I'll do all of them. No, not all of them. Some of them are easy. Send me in the group chat which ones you want me to do. This is not a democracy.
I think we should just start with like one, go in order, and then whatever we have time for, we have time for.
Okay, fine. So in a triangle, a Sevian is any line segment with one endpoint on the vertex. Let me draw a triangle. Oops. So here's a triangle. Let me make it more scalene.
Professor, you can use the shape. They have a triangle in option.
Yeah, but that's too easy, don't you think? That's just too easy. Why would I do that? I didn't know that. Thank you. Okay, so here's my triangle. Here's the Sevian. I think it's AD, right? Oh no, of course CD is the Sevian. Why would I do it correctly? Curses. Did anyone do this problem?
Yeah.
Yeah, good. So it's doable.
I mean, I think so.
So CDB is 80. CDB is 80. Let's see. ABC is 50. ABC is 50. And remember, we're in hyperbolic geometry. DCB is 30. DCB is 30. This is a 50. It's 30. ACD is 20. ACD is 20. And ACD is 20. Oh, no. Wait. And CAB is 30 or 40. Okay, good. This is a very easy problem, actually. This is a very easy problem. So you're asked, find the defect of which one? ACD, of triangle ACD. And you just need to know what a defect is. ACD, it's just 180 minus the respective angles of this triangle. So let me highlight this triangle. We're trying to find the defect of ACD, this guy here. So first, you want to do it using the additivity property. Or no, you want to use the linear pair axiom, but without using the additivity property. Okay, fine. Well, linear pair axiom says, since this is 180, since angle CDB is 80 by linear pair axiom, we know that ADC must be 100. So that means that delta of triangle ACD, by definition, is just going to be 180 minus 20 minus 40 minus 100, because we just found out that this is 100, which is equal to 20 degrees. So that's one way to do it. And if hyperbolic geometry is consistent, well, no, that's not true. So long as hyperbolic geometry is consistent, we should get the same answer two different ways. So now we'll use the additivity property. We know that by additivity, now we're not, suppose you didn't have the linear pair axiom. By additivity, we know that the defect of this big triangle, ABC, decomposes into the defect of ACD and CDB. So this is equal to the defect of ACD. Oh, sorry, I should have said, oh yeah, ACD plus the defect of CDB. Okay. Oops. Sorry, hold on, my tablet's not working for some reason. Sorry about that. Can everyone still see my screen?
Yes.
Okay, thank you.
Yep.
So, okay, fine. So this thing is what we're looking for. Sorry, I'm going so slow. This thing is what we're looking for. This we can get. We just use the definition. This is 50, this is 50, this is 40. So that means that the defect here is 40. So this means that 40 is equal to the defect of ACD plus the defect of CDB is, let's see, this is 30, 110, 160. So this is 20, yeah, 20. Oh, and so that means by simple algebra, you get that the defect of triangle ACD is 20 degrees, right? Is that clear? Is that, I skipped a step to go from here to here, but I hope it wasn't too fast.
Seems pretty straightforward.
Yeah, it's pretty straightforward, right? It's just you have all this jargon, you have the Sevian and the defect and the blah, 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 but it's not so hard. So long as you know the definitions. Okay, fine. Can I erase this? Can I?
Yeah.
Yep.
Actually, because this is being recorded, I'll go a little faster. How do I erase all of this?
It's easier to just move your screen up so that you have more white space.
So
Yeah.
like this?
Yeah.
Okay. Do you guys have to follow me everywhere that I go, or you can just see where I move to?
It goes automatically. Yeah,
Okay, great. Okay, good. I'm worried it might slow down my computer if I just have too many notes, but we'll see.
Be on the server, not on your computer, so it's not stored locally.
No, but my computer has to interact with all of those things. I imagine that I imagine that it matters. Okay. So assuming absolute geometry in the hyperbolic parallel postulate P2, prove that given a point C and a line AB with C not on AB, there are infinitely many lines through C parallel to AB. So I think we proved this one. Does anyone want me to go over 2 again? It's in your notes, but if you want me to go over it again, I will.
Yeah, or honestly, out of all the questions, I still feel like I'm weakest on this.
Okay, so recall, all right, fine, that's fine. So axiom P2 says that given a line M, so here's my line M, and point C, I have at least two. I have at least two lines that are parallel to L. Sorry, parallel to M that pass through C. Okay. So let's call this L1 and L2. These are my two lines. And you're supposed to prove that there are infinitely many lines that satisfy this property, that they pass through C and they're parallel to M. Okay, so how will we do this? We're going to use the crossbar theorem. In particular, we're going to let I'm going to make a new line. What should I call it? Call it R after Ryan. So let R, here's my new line R. It's going to be between L1 and L2, and I'm going to assume that it actually does hit M somewhere. Let's say at point D. Okay. So let L1 be between, let R be between L1 and L2. These two rays here, okay? Okay. Assume that R intersects M at a point D for contradiction. Okay. I'm doing a paragraph proof. You can do a paragraph proof. So long as you have a picture, you can do a paragraph proof. That's fine. Okay. Who remembers how you do this? I also give you the crossbar theorem, so you need to employ the crossbar theorem, right?
Yeah.
What does the crossbar theorem say? Crossbar theorem says, actually, how did I give it to you? I want to use the right. If D lies on the interior of BAC, so here's crossbar theorem says that if you have this, you have a point D that lies on the interior of this angle, and you connect it up to A, which is the common point of these two rays, then D has to intersect AD, sorry. AD needs to intersect BC at a point. That's just a fact. Okay. Is this all right with everyone? So, what's the, and this is an if and only if statement, basically. Sorry, give me a second here. Okay, this damn thing isn't working. Okay, there we go. So we have the crossbar theorem. I'm sorry, it's a little disorienting. Okay, fine. So I stated the crossbar theorem, and we're proving, we assume this. So now, let me just draw the picture. Here, C is going to be our common point. You have L1 and you have R here. Wait, am I messing this up? No, I think I'm right. So you have R here, the line R, and you have L2. Okay. You know that R and L2 are parallel. Okay. Oh wait, do you know that? Hold on.
You know that they are not because they both pass through C.
No, they can't be. Right. Oh, and then we're going to prove that they're the same line. Right. Or are we? No.
Are we
Oh, yes, we are.
extending the line that you have one line connect with C and AB that prove that the CR and CL2 and the C another horizontal line that they
We could do
are.
that.
I forgot.
If we have if we make this horizontal here, if we make this altitude. Is that how I did it? I don't think that's how I did it though.
That's how you did it in class.
Oh, really?
Yeah, yeah, you
I
putting
feel like there's a
the
different way. Okay, fine. So that's how I'll do it here.
The bottom
Okay.
of your betweenness relation was the CE.
Oh,
yeah
okay.
CR and
Hmm.
CJ.
Okay, so never mind. I messed up. Okay. Okay,
No,
so
I think you still had that part, and then you had
right. This must be so.
Which one is that?
Okay. Wait. Hold on. Curses, this thing's not working. Okay, there we go. So let it be that CE is between, sorry, no, L2 is between CE and R, and assume that R intersect M is equal to D. Okay, well, by crossbar theorem, we know that L2 by crossbar theorem. Look, so in this picture, I messed up, sorry. This is CE, that's this line here. This is L2, that's this line here. And this is R, that's this line here. And ED, so this is, yeah, ED, so this part here is this. So that means so that means L2 must intersect DE. By crossbar theorem, we have L2 must intersect line ED. But we assumed, but not we assumed, but L2 was parallel to line ED, which is equal to M. And that's a contradiction.
Mhm. So what was your question again? Because I just got in.
It's homework 2. It's
Okay.
question 2 on the homework
Mhm.
or on the review sheet.
Okay. It's on Blackboard?
That's right. Yeah.
Okay. Mhm.
Oh, yeah. It has to be on Blackboard. I put it on Blackboard.
Yeah. I think today, can you post all the homeworks that needed to be done for the class on Blackboard? Because I don't see all the homeworks. I only see two
Well, I
homeworks.
put them on the board.
Okay.
You can email me if you need
Okay. Yeah, I'll email you.
that list.
Mhm.
Okay. Anyhow, so that was number 2.
Wait, before you move on, so then to say that there can be infinitely many, you just say there are infinitely many interior points that you can find?
No, that doesn't. No. That's not necessary. It's not that you need infinitely many interior points. You just need one.
Well, you're proving that there are infinitely many parallel lines.
Yes, but the way that we're doing that is we're saying we know that we have 2. Given any 2, we can always construct a third. And then you only really need one interior point to construct the third line. And then between any other 2 of them,
You do another one, yeah, and then you do it, yeah.
keep doing that ad infinitum.
Yeah.
Does that make sense, Haley?
Yeah, it's actually an
Should I draw another
inductive.
picture?
No,
It's
that
actually
makes
an
sense. It's
inductive.
just you need to say that, or is it sufficient to?
No,
leave-
you don't need to be so explicit.
Okay,
Mhm.
that's good, thank you.
3. At this stage, it's rather cumbersome to be. It's not necessary to be so. I don't know. It's rather stultifying is all. If I make you list every implicit assumption.
Yeah,
Okay.
got it.
Oops. Okay. Recall that the area of a triangle is defined to be k times the defect. Prove that two congruent triangles have equal areas. That's easy enough, right? So prove that two congruent triangles have equal areas. Let triangle ABC be congruent to triangle, XYZ. Low, wake up. Good. Then angle A equals angle X, angle B equals angle Y, and angle C is equal to angle Z. I should put the measure of the angles. Oh no, I can just say that they're all congruent.
Mm-hmm.
Good. And then, okay, so let's calculate the defect.
Mm-hmm.
So the defect of ABC is just, what is that equal to? That's equal to 180 minus the measure of A,
Mm-hmm.
minus the measure of B, minus
Minus
the
negatives.
measure of C,
Mm-hmm.
which is equal to this thing. When you make the necessary substitutions.
Mm-hmm.
Oh, but that's just equal to
Mm-hmm.
the defect of triangle XYZ.
Mm-hmm.
Okay, so if you have this equality,
Mm-hmm.
so you have this equality here. By algebra, you can say, you can just multiply by k on both sides.
Mm-hmm. Mm-hmm.
K is a constant. Uh, is that clear? Is that proof clear?
Mm-hmm.
Does anyone have any questions about this proof? Did I go too fast? Did I go over it again?
What do we
No.
do
Good so
regarding
far.
the part where it says, is the converse necessarily true?
Yeah, so I was going to get to that. So
Oh.
is the converse necessarily true? Here we
Mhm.
prove that if two triangles are congruent, then their areas are equal. But can you have two triangles? Question, what's the converse? The converse is
If you have the same areas, do they mean they're congruent?
if A1, say, is equal to A2, does that imply that the triangles are congruent?
No.
Let me write this actually. If the area of ABC equals area of XYZ, does that imply that these two triangles are congruent? And the
I
answer is
think
no.
no. In fact, you can see that you can make a right triangle and you put half of it and put on the other side, you make a isosceles triangle. That is not where the two legs are not the same. You can.
Well,
You can
does that
see
mean that the defects are equal?
No. I'm not saying that. I'm just saying if the two areas are the same, doesn't mean they're congruent. But the defect might. I don't know about the defect yet, but since the defect affects the shape, that could be something that is true somehow, right?
The defect, I'm not quite sure what you're asking.
Okay.
But let me give a counter example.
Okay. Mhm.
So let let angle A be 90, let
Mhm.
angle B be 10, and
Mhm.
angle C equals to
Mhm.
10. Say. Oh no, yeah, that's fine.
Mhm.
And let angle X be 90. No, let's say, yeah, that's fine. X is
Yeah.
90.
It's just the subtraction, you have to keep it constant.
Y is 11,
Mhm.
and angle Z is 9.
9. Yeah.
So look, if you were to calculate the defect here,
Mhm.
defect, the defect of ABC
Mhm.
is equal to, let's see, this is 110, so 70, which is equal to the defect of triangle XYZ,
Mhm.
as you can see. You just do 180 minus 90 plus 11 plus 9. So these two areas are the same,
Mhm.
but clearly, because the angles are different,
Mhm. Therefore, they cannot be congruent.
your free meeting will end in 10 minutes. What?
Yeah, because it's
Hold
45
on.
minutes.
Wait,
You
wait,
have
wait,
to
wait.
renew it.
Wait. They're gonna kick me out of my Zoom meeting? What? But Hunter College paid for Zoom. That doesn't make any sense.
But Professor, do you use the portal from CUNY first sign in? If otherwise,
No, but what do
maybe they count as your own account, not the CUNY account.
Yeah, you're probably gonna have only 45 minutes.
no, but this is my CUNY account, and I'm an instructor at CUNY. What? Nobody told me this. This is horrible. Okay, anyway, but clearly, to hell with Zoom. You guys should have came to my apartment like I said. Fine, but clearly, triangle ABC is not congruent to triangle XYZ. What kind of dystopian message is that? Okay, whatever.
It's not congruent, right?
Oh, not congruent. Thank you. Not congruent. Because the angles are different, so those can't be the same triangle. Okay. Is that all right?
Yes.
That's easy, right? You just have to give a counterexample. So wait, will the same link work if we come back in? Or do I have to make a new link and send it out?
Yeah, you're gonna have to make another link.
What? This is ridiculous. This is preposterous. This is absurd. Okay, whatever. Let F and G be isometries. F, G, isometries. Oops. Prove F composed with G is an isometry. Okay, so to prove that something is an isometry, recall the definition of an isometry. F is an isometry if and only if AB is equal to A prime, B prime. So it's a distance preserving map. So let So suppose that F maps A to A prime, G maps A prime to A double prime, and also F maps B to B prime, and G maps B prime to B double prime. Then you know A B is equal to A prime B prime, because F is an isometry, and you know A prime B prime is equal to A double prime B double prime, because G is an isometry. So AB is equal to A double prime B double prime. So, oops, I should have said, sorry. All right, so G composed with F is an isometry. Sorry, I should have said F composed with G. Ah. So, okay, I'll make a new link and send it to you on Blackboard, and then we'll reconvene like in 10 minutes. I didn't know about this. I'm sorry.
Yeah, it would
I
actually.
thought CUNY paid its bills.
No, it doesn't work that way. Even for other classes, it has to be renewed every 45 minutes.
No, but it never used to be like that before. I could be on Zoom for
Yeah, forever.
forever if I wanted to be. That's dumb.
This is recorded, Professor, right?
Yes.
Or how are we gonna have access to it? You're gonna send it. You're gonna post it on Blackboard.
I'm
or
gonna
you're
post it
send
on YouTube, and then you have to go find it.
Oh, you're gonna give us the link, right?
No, you have to find it. You have to find my YouTube channel. It's more fun that way.
I know.
Let I be an isometry. Prove that I preserves betweenness.
Mhm.
Did everyone do this question? I feel like I did this in class.
Yeah, I think you're gonna use the definition of betweenness, and then you know that
Right.
you're
So you
gonna
want to
have
show
the sum. Yeah,
that
you're gonna use the
A,
definition.
B, C implies that implies
A
this.
prime.
Oops.
Yeah.
Uh,
D prime, C
D
prime.
prime. Good.
Mhm.
Okay. Well, this is a multi-step proof. I don't think I could do it in 3 minutes.
Okay.
So let's see. Is there anything I can do in 3 minutes? Oh, okay. Let's do number 6 together. Number 6 says, give a short response to each question. You do not need to provide a formal statement, reason, proof. In Euclidean geometry, an equilateral triangle has angles that measure 60 degrees. Is this possible in hyperbolic geometry? What's your answer? What's your answer, guys? No. Okay, Ryan, why not?
Because 360-degree angles makes 180, and in
80,
hyperbolic it has to be less than 180.
Less than
Right.
180.
60 plus 60 plus 60 is 180. Oops. Which is
But
impossible.
it doesn't mean you. Yeah, but it doesn't mean you cannot have an equilateral triangle. You can. It's just that it's not going to be
Right.
mirror that.
But you can't have one with 60 degrees. Okay, good. Fine. Oops. Now let's do number B. That was B. 2 minutes left. Suppose you knew that the sides of a triangle in hyperbolic geometry were all congruent. Can you then conclude that all of its angles are congruent? Why or why not? Who has the answer for this one? Suppose all the sides in a in a triangle of hyperbolic geometry were
Mhm.
congruent, could you then conclude that all the angles were congruent?
Because the sorry.
Mhm.
We know that the perimeters could go to infinity. It's possible that the perimeters could go to infinity. So yeah.
Is it yes because of the scaling inequality?
Exactly. Yes,
Yeah.
because of the scaling inequality. We know that from our regular geometry days, let's say that you have something like this, say,
Mhm.
if this guy is smaller than, let's say, this guy, then the opposite angles are smaller,
Mhm.
right? This angle has to
Mhm.
be bigger than this angle, say. We know that that's true. And in fact, if all the angles are congruent, then the same goes for the angles as well.
Mhm.
If all the sides are congruent, then the same goes for the angles as well. Good. So by scaling inequality, I'm going to write that down. We have less than a minute, but
But it's also possible for the sides to go to infinity,
what
as
do you
far as
mean
an
by that?
ideal. Because in hyperbolic geometry, you can have
Oh,
a
you're going to be
finite
cut off.
area.
So let's just let's reconvene in just a moment. We'll
Okay.
reconvene in about 10 minutes. I'll send you the link and then
Okay.
we'll meet back up at 7:50. Sorry about this.
Mhm.
Okay, bye guys.